but in past years, it's been sort of outside, and then when we start training, which it will, everybody runs inside. So we'll go over there and figure it out. I apologize for having to tell you this, okay? If any of you have read Catch 22, you will appreciate, and if you haven't, I can tell you about it at dinner. Bring your name tag, and you have to have a photo ID, okay? Blame me. But you have to have these things, and we'll see you whenever. What does it start? 6:30, something like that. Okay, good. Okay, take it away, Freddy.
Okay. So after the small detour we had yesterday, today let's go back to twistor space. Now let me remind you what we said. We said that Penrose was very excited about the idea of constructing a space where null rays were fundamental, and therefore they had to be the points in the new space. So this is going to be space-time. And here we're going to have twistor space. So to describe this, you look at the celestial sphere, or where the null rays are coming from. You choose a direction, and you choose a point where the ray passes through. Now, a way to describe the ray would be by having an equation of the form so any point, so you choose a reference point x in a space-time, and then you say my null ray is going to be given by choosing a null direction and parameterizing it with a real variable t that goes from -infinity to infinity. So this is a parameterization of this null ray. So note the following. If you now take the difference of these 2 points, so these 2 points are null separated, so they have to be given by, or they have to give a null vector. And this is the way we describe null vectors, if you remember. Okay. So now you have to make a choice, and Penrose made a choice. So the choice is to dot this equation with lambda of this vector here. And then what you get is the following. You get 0. You could have done the same thing with lambda tilde. And if you do it, you get something that Penrose called dual twistor space. But we're not going to discuss that. So we're only going to consider twistor space, which is the one that you get when you dot it with the lambda. So Penrose realized that this meant that along the null ray for any t, this quantity was constant. So this is an spinor that somehow is part of the data involved in this null ray. And therefore, it should be given a name. So this object is what he called mu alpha tilde. Okay? And this is what we wrote last time as the incidence relation. Now, something I didn't mention is that this equation looks a little bit complicated, but it has a beautiful property that Pedro also mentioned in his lecture yesterday, which is that under conformal transformations, something very nice happens. Even though conformal transformations act in a very difficult way on the x, they act in a very nonlinear way on the x, the way they will transform the combination lambda with mu is absolutely spectacular. So it's just going to be, so conformal transformations will act on this object as an SL4 transformation. So this object, under conformal transformations, you can exchange mu's and lambdas. So mu's and lambdas should be thought of as a single unit. And this is the reason why Penrose introduced a notation for this object. Now, of course, if you have an object Z, or you have an object that you can call rho Z, where rho is a non-zero complex number, both objects will describe the same null ray. So instead of having that the space of null rays naively seems to be C4, you have to mod out by this action, okay? So you have to mod out by this C star action, and this is nothing but a CP3. So we have our space-time, and we have CP3. And a point here describes a null ray here, okay? Now, I want to try to invert this map. I want to ask, instead of looking at a point here and seeing what it looks like here, I want to find a point here and see what it looks like here. Well, how can you define a point here? Well, something that you can see on this side related to this point is the space of all possible null rays that cross this point. What are all those possible null rays? Well, they will be described, or they will be given, by all possible twistors, so the Z's are called twistors, that satisfy this relation for that particular point in space-time. Well, clearly, for any value of the spin or lambda, I can always find a mu such that this is satisfied, or that's the definition of the mu. So the space of all twistors that satisfy this equation for a fixed x is a two-dimensional submanifold, okay, of C4. But when I mod out by the C star action, it's a one complex dimensional submanifold of CP3. And that's called a line, or a CP1, okay? So to every space-time point, there is a CP1 associated to it. Now, if I want to describe in the most compact way my space-time point, people who do algebraic geometry don't really draw this like this, and I think I'm going to do it the way people do it in algebraic geometry, and you will see why it's more convenient. They call a CP1 a line, so they draw it like a line. So there is this line related to the point in space-time x alpha and alpha dot. Now, if you want to define a line, what is the data you have to give me? Well, everybody knows from high school that to define a line, you need 2 points on the line. So let me call these points Z and Z prime. So these are two twistors that belong to the same line. So let me call the first twister lambda mu, and the second twister will have lambda prime and mu prime. This twister has to satisfy the same equation with the same x. How many equations are these? 2 equations. And these are 2 equations. Okay? Now my data are the 2 twistors Z and Z prime. Now we have 2 equations here and 2 equations here. So we have 4 equations. And how many unknowns we have? Remember that what I want to do is to invert the map. I want to find x as a function of the twistors. So you have x has 4 components, right? It's a 2x2 matrix, so it has 4 entries. And I have 4 equations. They are linear equations. So very difficult to solve. So you need Mathematica. You put it in Mathematica, Shift Enter, and after a few seconds, if you're lucky, you find this. Okay? So that's explicit formula for the space-time point if you're given two twisters. Now, any two twisters on that line, we have done the same job. Okay? So a point in twister space is connected to a pair of twisters modulo a transformation that doesn't change the line if you're given these 2 points. Now, that transformation, if you think about it, is any linear combination of the two twisters mapping into another two twisters that belong to the same line. That group is called GL2. You can apply any transformation to the two twisters written in this way now as a 2x4 matrix. If you apply a GL2 transformation, you mix them up, but you don't change the line. Okay? So 2x4 matrices modulo GL2 describe a space that mathematicians love, and that space is called the Grassmannian of two planes in C4, or also written as GR24. So we have just learned that Minkowski spacetime is also equivalent to the Grassmannian of two planes in 4 dimensions. But we're not going to use that. All we're going to use is this formula. Now let's go back to Park and Taylor. I hope you all did the exercise. So let's move over here. So remember, we have our amplitude. Now I want to write this full amplitude. With I and j negative helicity, and the rest are pluses. This is Park and Taylor. So this amplitude I'm going to write as this. So as I mentioned, I'm sure you all did the exercise, and you have proven already now that this formula is correct. And we have the delta function of momentum conservation. Here I'm mixing up a little bit the notation. I use calligraphic A for the full amplitude with everything, with color structures and partial amplitudes, delta functions, and everything. Now I'm considering a hybrid. This calligraphic A for me today means a partial amplitude, but the partial amplitude dressed with a momentum conserving delta function. Okay? So it's some way halfway between the two. So this was Park Taylor, and now we follow Witten in 2003 and write this as an integral over the space-time e to the I alpha alpha dot sum over a lambda lambda a tilde, and we construct a new object a tilde, which will now depend on twistor variables. But we don't have the right to call them twistors yet. The reason is that we don't know if this whole thing that we're going to write only depends on the full twister, or if it depends individually on lambdas and mu's by themselves. Look at the transformation. It's non-trivial. So recall that this was defined as a Fourier transform over the lambda tildes of each particle of the function that we had here. I'm always very consistent, yes. And I thought about it. And I thought, well, Pedro is going to tell me, so don't worry. Okay. For each one of them, we introduce this, or if you want, we can put the sum over A here. So what's the answer? The answer, again, is just our twist, our part-Taylor factor, the integral dx4, and we have a sequence of delta functions imposing these conditions. Okay. Okay, the first step, what we're going to do is use this transformation. Okay? So let's use that transformation in this equation. So this formula now looks like this. Mu A alpha dot minus, so I'm going to use that formula over there, and this is going to be dotted with the spinors that appear there. So we're going to get something that looks like this. I hope you remember my notation that A stands for lambda A. Maybe I'll write it. Yes. Divided by lambda prime. And then we have mu alpha dot minus lambda prime, lambda A, lambda prime, lambda, mu prime alpha dot. Have I made any mistakes? You say yes, because there should be a minus sign. But note that the denominator is slightly different. I switch prime, lambda, and lambda prime conveniently here. So I also paid a minus sign that fixed the minus sign that came from there. Okay, this is very nice. So if I only knew how to change the variables here as well, I'll be in business. So my first attempt would be to say that this measure goes into this measure. Let me write the full twister z and the twister z prime. But that's clearly too naive. And the reason it's too naive is that this measure is over a 4-dimensional space and this one is over an 8-dimensional space. So that's clearly wrong. So I'll fix that problem by saying that I have a redundancy here in the description of the point in space-time, but I know exactly what the redundancy is. So as a good physicist, we do something that mathematicians we hate. And we divide by the volume of GL2. Even though GL2 is an infinite dimensional group, is a group that has infinite volume, we just divide by it. What we mean by this is that we have to gauge fix the GL2. So we treat this as if it was a gauge theory, and we have to gauge fix this. But once we do, we go from 8 down to 4. So this at least has the right dimensionality. But it's still wrong, because if we rescale the twistors by something, remember the twistors live in CP3, so if we rescale them by rho, if we rescale z and z prime by rho, x doesn't change. It shouldn't, right? But this object changes. So we have to fix that. Moreover, there is also something else that is wrong. This object is not conformal invariant, and this object is conformal invariant. So we have to break conformal invariance on this side, fixing the scaling, and the only thing that you have at your disposal basically is lambda prime to the 4th power. So that's the correct measure. Okay? Now you look at this, and if you have played with spinors or 2-dimensional vectors in C2, you will notice that these objects here are nothing but the coefficients of the expansion of the spinor A in terms of the bases lambda and lambda prime. In other words, this is a true identity. Sorry?
The prime and prime terms.
Oh.
Offline you want mu prime
On this one, yes. Yeah, that's right. Yes. Well, that's clear from the definition over there. So Pedro is the best student. So you should be ashamed that Pedro is actually the best student here. No, good. Everything was going to break apart at some point. So
it's a true identity, okay, then I could answer.
Yeah, you couldn't. Very good. It went against your principles. Yeah, no, it's good. I mean, accepting that statement, we have been accepting that you didn't know that it wasn't a true identity. Okay, very good. So now this is a true identity. And you see that it looks very beautiful because this combination is a twister. This combination is a twister. And this combination is also a twister. So if we were able to write everything in terms of these combinations, maybe we'd be in business. So one way to do that would be to use the following identity. Let's just give names to these coefficients. Let's call them, say, sigma A1 and sigma A2. And introduce them as auxiliary variables that you integrate over with a delta function that actually imposes that constraint. I told you that these were the coefficients of this, so this was an identity. So if I impose this as a constraint, these delta functions will force the sigmas to take exactly those values. But I cannot just stick this into my formula for the amplitude unless I fix a Jacobian so that it's equal to 1. Now I can stick this into the formula and get a new formula for A tilde, which is going to be now the integral over the sigma A, the sigma A2. So I still have the part-Taylor factors, ij to the 4th, 1, 2, all the way to n1. What else do we have? We have the integral over the twisters. And what else? And we have what I wanted. Each of these delta functions combines with one of these delta functions. Remember, these delta functions ended up being these delta functions. On the support of these ones, I can replace as well these factors by sigmas, and I combine everything into a beautiful delta 4 of twisters. Yes? Is there something with? Sorry, just taking a break from with the noise. Okay. So what happened with the Fourier transform? Yes. That's right. So the standard answer to that question is that we can work in a different signature of a space-time, in 2,2 signature. You do a weak rotation, not in the direction that you usually do it, but you take another space direction and you do a weak rotation. So you go from 3,1 to 2,2. Then in 2,2, the Lorentz group is SL2R cross SL2R, and the spinors become all real. Lambdas and lambda tildes are now vectors in R2, and they become independent. And all this goes through. And this is not CP3, it's going to be RP3. Yes. So you were right, there was some math hidden in the whole thing. So this formula looks very, very nice. This object here is conformal invariant, is SL4 invariant. But how about the rest? It doesn't look like something that is conformal invariant. The reason is that it depends on the lambdas. It doesn't depend on the twistors. Okay? So we want to fix that problem. Well, it's not something that you can fix. It's either true or not true. Okay? So let's see if the problem actually goes away by itself. I'm not going to hide anything or push the thing to do anything that it doesn't want to do. So let's try to compute these brackets that appear all over the place. Well, I said I wasn't going to do it, but let me just define again what this is for you. Okay, so every time you see AB or 1, 2 or something like that, it means the bracket of the corresponding spinors. Okay. Now, on the support of the delta functions, I can replace these spinors by this combination. And what do I get? Well, clearly, if lambda and lambda prime were equal to each other, I should get 0. So that means that this object contains a factor of lambda and lambda prime. But also, if the two sigmas is the sigma, well, the sigmas now look like a small 2 vectors. So clearly, if these two guys were linearly dependent, so if one was proportional to the other, I would also get 0. So whatever has to go here has to be the determinant of this object. Okay? So this is too long to write, so I'm going to define it to be this bracket. Okay? So now by this bracket, I mean the determinant of this 2 by 2 matrix made out of the sigmas of the corresponding particles. Now let me make this substitution everywhere. So my object now becomes an integral over all possible a's okay. Now I make the substitution for the part-Taylor factor. In fact, so now I should write the integral over the twistors here. Times, now I can make the substitution, right? Because this is going to depend on lambda and lambda prime. So the substitution will give me the same part-Taylor factor, but now written in terms of these determinants. But now this thing is going to give me also some power of this. And the power that I'm going to get is lambda prime to the 4 minus n power. And Pedro wasn't paying. No, he knows, but he didn't tell me. He didn't want to say. Joao also noticed. Come on, there is something still missing in this formula. Somebody else has to tell. It cannot be that Joao and Pedro. Yeah, exactly. 1 per delta function that I introduce. And I have a product over A from 1 to n. So I introduce n of these things. So I got a factor that I didn't write of lambda prime to the n. Why did I notice a factor now? Well, because you see now what happens, a little miracle. This thing cancels completely this thing, and I end up with a product from A to 1, from 1 to n, of delta 4 ZA minus z prime minus z. So now my formula is a formula that only, all the external data only enters through the twistors. So I have shown that the part-Taylor amplitude is conformal invariant. So part-Taylor. So the part-Taylor formula is SL4 invariant. Which is the same as saying that it's conformal invariant. Okay. Very good. I mean, this is all very nice. So let me actually delete this from here. Well, but if this was the end of the story, I mean, the formula is beautiful, but not that beautiful to justify the whole lecture. The point is that now this formula gave the idea to Witten of how to generalize this to other amplitudes. Remember that amplitudes in 4 dimensions were classified by this number k that tells you how many negative helicity particles were in the amplitude. In this case, the part-Taylor formula corresponds to k equals 2. So if you were someone familiar with algebraic geometry, you would realize that this looks as if it was, you had CP3 given by the twistors, and these delta functions are somehow mapping points here to twistors here through that map. So you would say that this is a linear map from this space to this space. So this is a map of degree 1. But you wouldn't be satisfied, because nice maps, the nice maps that you know, because you know algebraic geometry, are maps between complex manifolds. But this doesn't look like any complex manifold. These guys are random things that I put in by hand. Okay? Now what I want to do is to make a slight transformation which does the following. This GL2 is acting on Z and Z prime, right? That's how we discovered it, because we had the space-time, we had to mod out by this. But note that Z and Z prime are locked to sigma and sigma 1 and sigma 2. So if you perform a transformation on Z1 and Z2, you can undo it by doing the opposite transformation to sigma 1 and sigma 2. So you can also think that this group is not acting on the twistors, but is acting on your sigma variables. So I'm very happily going to delete this from here, and I'm going to put it here. Not only that, I'm going to recognize that GL2 is also SL2 cross the volume of C star. Okay? And recognize that SL2C is precisely what I have to mod out n mark points on a sphere so that I can declare that that sphere is a complex manifold. Okay? So now we are done in the sense that this has become a CP1, and now I am embedding this CP1 inside CP3 using a linear map. Of course, anybody who knows string theory would say, well, in a string theory, we have CP1s with marked points. And every time you talk about mapping this into a bigger space, you call the bigger space the target space. And this object will be your roll sheet. However, you know that a string theory is a very constrained object, right? In fact, so you all have learned that to make the worldsheet theory a conformal field theory would require you to make this space, say, depending on the matter that you put here, 10-dimensional or 26-dimensional. So it seems that we're going to be in trouble. There is no way to make a consistent string theory if we map it into this space that has 6 real dimensions and not 10. Okay? But there are models of a string theory that are not full string theories. They are called topological models. And they come in two varieties. There is the A model and the B model. And it turns out that the B model seems almost to be happy to live on this space. Okay? So Witten knew that this model could almost live in a space or in a target space that was CP3. The only problem is that the B model is a little bit picky. It wants spaces. They could be 6 real dimensional, no problem. But as a complex manifold, they have to be Calabi-Yau. So that's a little bit annoying because CP3 is not a Calabi-Yau manifold. So it's a 3 complex dimensional manifold, but it's not Calabi-Yau. So CP3 is not Calabi-Yau. Sorry? The A model is ruled out because it doesn't have, the A model depends very much on the cohomology of the space, and the space didn't have enough to support the fields that you wanted. So if this had happened to me, I would probably have stopped here and said, well, this doesn't work. But it didn't happen to me. It happened to Witten. So you say, let's try to cheat the B model and trick it into believing that it's in a Calabi-Yau space. So what Witten did in 2003 was to say that the CP3 has to be replaced by CP3/4. So he made it supersymmetric, and to be Calabi-Yau, you need precisely this number to be 4. What do I mean by that? You take your twistors, lambda and mu, and you extend the space with Grassmann odd directions. How many of them? Well, it's not up to you. It's up to the B model. And the B model chooses as critical fermionic dimension exactly 4. So you have to add 4 fermionic directions. So you add eta 1, eta 2, eta 3, and eta 4. Remember, these guys were alpha and alpha dot, so they are 2-dimensional, and this is a 4-dimensional object. And these variables satisfy this relation. They are Grassmann odd. Okay? So the bosonic dimensionality of the space didn't change. So this was regular twistor space, but now enriched with fermionic variables. Very good. At this point, you could have wondered, well, maybe you don't want a string theory, perhaps. But you could have tried to extend this and said, Well, what if I consider maps of higher degree? I can consider a map from here to here of degree 2, degree 3, and so on. You could have done that, but you could have realized very quickly that this formula that we wrote there wouldn't have made sense if you had done that. And the reason is that the scaling of the z's would have been wrong precisely because of this factor, which, by the way, is wrong. It should have been 4, right? So this factor would have prevented us from extending this map into higher degrees. Now, being obsessed with a topological B model actually buys you something else. It tells you that you can write down the formula in the super twistor space, and the formula, this particular formula, will automatically take into account this factor here. And the 4 is not an accident. The fact that there is a factor of 4 is related to the fact that there are exactly 4 fermionic directions. So I'm going to write for you the formula that ends up taking into account that factor. So I'm going to write it like this. Now, I only have the analog of the Part-Taylor structure multiplied by, now my twistors are objects that live in C4/4. I mean, this is a C4/4 object. And remember that I send the scaling into this other part of the object. So I'm going to have Z and Z prime, and the product from 1 to n of the delta functions, which are now supersymmetric delta functions. So these are delta functions for each one of the components of this object. Okay. Now, this formula also has some other properties, which the original formula didn't have. And one of them is that now this is manifestly invariant, not only under SL4, but under the supergroup extension of it. So this object is manifestly superconformal invariant, which is what it was supposed to be doing, because after all, we're computing now amplitudes in n equals 4 superjumbles. So somehow the n equals 4 ended up being the critical superspace dimension for a string theory. Okay. Now you would say, well, but where is my little Part-Taylor factor, this ij to the 4th? Well, what that object is, even though it looks super fancy, is nothing but a generating function for all possible amplitudes with different helicity configurations, but with k equals 2. What I mean by that is that this object is nothing but the following. It's a generating function that now depends on lambdas. If we go back to momentum space, lambda tildes, and these variables etas. And what I've done is said, well, imagine that you have the amplitude where 1 and 2 are negative helicity. So I'm going to multiply them by eta 1 and eta 2 to the 4th, plus the term where 1 and 3 are the ones that have negative helicity. So I'm going to multiply them by eta. So this is eta of particle 1, and this is eta of particle 2. To the 4th means that I'm multiplying all 4 components of this object. So here I have 1 to the 4th, and eta 3 to the 4th, and so on. So my ij guy is going to come multiplied by the etas of the ith particle, all of them, and the etas of all the particles, of all the etas of particle j, and so on. And very nicely, they are all divided by the same denominator. So this object that we have computed there in momentum space becomes a generating function that contains all amplitudes at once. But it also contains mixed things. What could they possibly be? So when we expand all the etas, and we just go crazy expanding as polynomials in etas, we will also find terms that mix the etas of several particles, more than 2 particles. So we will have less powers of this, but we could have things that look like 1, 2 square, 7, 9 square in the numerator, instead of a single power to the 4th. What could these amplitudes possibly be? Remember, now we are computing amplitudes in n equals 4 superjump mills. The theory has more particles than gluons. What else does the theory have? It has scalars. It also has fermions. So this object, as written there, is a generating function in what is called the k equals 2 sector of all possible amplitudes of scalars mixed with gluons and mixed with fermions. Yes?
When you went from this to the supersymmetric mode, how did you not think it would just
Yes, so this is something that I realized by the time I wasn't going to have time to do it. So at the end, we can do it on the blackboard during the break. Yeah, they ended up in the delta. I mean, that particular term is this component of that delta function after a supersymmetric Fourier transform, but never mind. Okay. Now we are ready to generalize this. What's a generalization? Well, you go back to this blackboard and you say, well, now I can define more general maps, not of degree 1, but of higher degree. We could do it in these variables, but it's a little bit cumbersome to do it in these variables sigma a and sigma 1. These are the inhomogeneous variables. Sorry, the homogeneous variables. So before we do it, let me change to the inhomogeneous variables, where the transformation is going to be slightly simpler. Otherwise, it would take too long to write. So here it is. We did it just the day before yesterday, I think. Let me introduce these new variables. So these are the homogeneous variables on CP1, and this would be the inhomogeneous. Well, let's just do it. What happens to our formula? So our formula becomes integral from 1 to n dta. So we can just make the change of variables. That's not very difficult. And we get a ta as part of the measure. We divide by the 2 volumes again. Then we make the change for each of these brackets. This becomes ta times tb times the difference of the inhomogeneous variables. So how many powers of ta would I pick from the part-Taylor structure when I make this substitution? How many powers of a given ta would I get? Well, a given label appears twice. So I'm going to get 2 powers of each, which cancels this. So you get a measure that is very nice. It's dTA over TA. And the rest is, again, the part-Taylor-like factor, but written in terms of the sigmas. And here I get this integral, which I'm now getting tired of writing, probably you too. But what I want to say was that I was getting tired of writing it in terms of z and z prime. So maybe let me introduce another notation. Let me call this 0, and let me call this 1. And then we're going to have the product from 1 to n, delta 4/4 of ZA minus TA of Z0 plus sigma A Z1. Now there is something very beautiful about this integral dTA over TA with this thing here. If you wanted to say that 2 objects were equal to each other up to a scale, meaning you want to define something on CP3 really, you couldn't say that 2 twistors were the same, because that wouldn't make any sense. 2 twistors could have to be the same up to a scale. So the way to define a projective delta function would actually be to integrate dTA over TA, this object. Okay, so we ended up naturally with projective delta functions without even thinking. All right, so written in this form would allow us to generalize. Now we go back to this board and we erase this, and we think that each puncture is described just by an inhomogeneous variable, and it's going to be mapped into twistor space in the following form. So a map of degree D would correspond to taking this point and mapping it here as follows. So you get your twistor Z. If you had degree 1, this is all what you do, which is what we did over there. If you have degree 2, you don't have to think too much. You just have to extend it by 1. And if you want to have degree D, you just extend it by D. So this would be the way of mapping a CP1 into CP3 with a map of degree D. So this map covers the CP1 D times. What could the generalization be? So this was for degree 1. If we want to generalize this formula, the generalization is now obvious. So let me delete this from here and just put it, well, it has to stay here. So the generalization to any degree is the following. You remove this from here, you say this is now for any degree, you declare it. And here, you remove this measure, and you say, I'm going to integrate over all the possible ways of embedding. So this is what the fancy way of saying this is that you are integrating over the moduli space of maps, meaning that you are integrating over all possible ways of mapping. So you have to introduce all possible ways of mapping, and here you extend this to degree D. Is there a sound? The sigmas are integrated. Yeah, I made the change of variables. So the scale stays the same. The map only affects the inhomogeneous variables. Okay? So we saw that for d equals 1, we got the MHP amplitudes. Well, then the natural conjecture was that for degree 2, you will get k equals 3, which are called next to MHP amplitudes, and so on. So d is going to be k minus 1. So this formula basically realizes Nair's dream. He wanted to generalize the idea that the part-Taylor formula naturally lives in twistor space, and Witten was able to realize that vision in complete generality for the full S matrix of n equals 4 superyammians. Okay. Now the formula looks very nice and very impressive, but when you write it in momentum space and you want to compute something, you will discover that these delta functions end up being a set of polynomial equations relating the sigmas to the kinematic invariants. So these polynomial equations could be very complicated. Okay? So as a computational tool, it might not be as good as the BCFW recursion relation that I showed you yesterday. That's why one of the organizers wisely suggested that I should have introduced first the efficient way of computing things. And now I'm showing you this one. Now, why am I doing this? There is something that this formula makes manifest that BCFW, the formulas you get from BCFW, will not. And many other formulas that you get from other techniques will not. I already gave you the answer yesterday. Any ideas? Well, the Yangian is something that this formula doesn't make manifest. Conformal invariance, you can make it manifest using BCFW. If you do it supersymmetrically, there are ways of running it that will make that manifest. Just keep it. There is only a finite number of things that I've mentioned in these lectures. So you can just keep mentioning. The what? Cyclicity? Well, that's a good one. Yes, indeed. BCFW, when you write the formulas, the answers will not look cyclic invariant. They are, but they are not manifest. So that's a good point. It's cyclic invariant. That's along the right direction. So I'll give you another hint. Cyclicity of the partial amplitudes allowed us to realize that the full amplitude, when written with color structures, didn't require m factorial terms. It only required m minus 1 factorial terms, right? But yesterday, I also mentioned that all those m minus 1 factorial partial amplitudes were not all independent. They also satisfied other relations. What were those relations? Exactly. So they were the KK relations. So know that this twistor space formula has the following structure. Now I'm going to write it like this with k minus 1, just to remind us what the physical object is. So this object has the following structure. It has the structure of a measure times this sigma 1 minus sigma 2 all the way to sigma m minus sigma 1 times this integral here of the super twistors and so on. Now, what's the only thing in this formula that depends on the particular ordering we're choosing? Remember here, we're computing a partial amplitude, 1, 2, 3, up to n. Does this depend on the ordering? No, this is permutation invariant, right? Does this part depend on the ordering, on the choice of ordering? No. The only thing that depends on the choice of ordering is this tiny thing here. So out of all that complicated thing that will come from choosing different orderings and so on, this twistor space formula manages to confine the color dependence or the ordering dependence to a very tiny factor. So imagine that I define this function gamma, 1, 2, up to n, to be this very simple rational function of variables, of complex variables. Okay? Could it be, maybe life is not that good, but could it be that this function satisfies the KK relations? If this very innocent function, very simple function, satisfies this, if we were able to prove that, we would have proven in one shot that all partial amplitudes, full partial amplitudes in n equals 4 super Young mills for any number of particles and in any sector, no matter the sector, that they satisfy the KK relations. So that would be a way of making this manifest, the KK relations. Okay? So it's tempting to give you that as an exercise. It's so tempting that I'll give you that as an exercise. But I'll do one for you. I'll do the U1 decoupling identity. Just to give you a hint of how you could do it in general. So I'm going to write the U1 decoupling identity in a slightly different form from what we did yesterday, because the notation is a little bit annoying. So I'm going to swap, if you look in your notes, I'm going to swap n minus 1 and n from the formula that you had yesterday. So the U1 decoupling identity for my new function gamma is the following. I have 1, 2, all the way to n minus 1, n, and I'm going to move n in the different positions. So I'm going to have 1, 2, all the way to n minus 2, n minus 1. So note that n was here now it's here, and it's going to keep moving until it makes it all the way next to 1. I hope you agree that this looks more natural. I mean, somehow this notation is nicer. So this is what we want to prove. Is this true for that function? Even better, it must be true for completely unconstrained variables, sigmas. Okay? So it has to be just an identity, straight there. No constraints or anything. So if you see all these gammas, they have many things in common, right? But there is no factor that is actually common to everybody. So there is a factor, a given factor is common to everybody but one guy, right? So it's a little bit annoying that. So it's so tempting to factor it out that we should just do it. And the guy that fails to have that factor, we will put it in the numerator. Okay? So I'm going to put out all these sigmas, all these factors. And then if my gamma doesn't have anything, if my gamma doesn't have one of them, I'll just put it in the numerator to compensate for it. But I'm also going to do something slightly different from what you would normally do, which is to start with this guy and putting it here. I'm going to start in reverse. So I'm going to start with this guy. So if you write this down, you see that this gamma has everything except for what? Except for the first factor. So we fail exactly with the first factor. So we have to put it in the numerator. This gamma doesn't have sigma 1 minus sigma 2. But now this gamma also has stuff that are not here. Exactly 2 factors. And those 2 factors are sigma n minus 1 minus sigma n minus sigma 1. Now, if you multiply this by this, you get this gamma function. Well, it's not a gamma function, this function gamma. Now you do it to the next one, but now you see the pattern. All the labels are shifted. I think I'm sure. Oh, yes. Sorry. No, then I'm not sure. Yes. Yeah. Okay. Very good. Once again. Thank you, Pedro. So n and 2. Or 2 and n, it doesn't matter. Or no, n and 2. Yes. Good. Now we shift everything. Now we have 2 minus sigma n minus sigma 3, plus, plus, plus. And the last one, so what's the thing that the last one is missing? Is n minus 1, 1, sigma n minus 1 minus sigma n, times sigma m minus sigma 1. Okay? And the question is this 0? So here I'm going to introduce a trick that Homogeneous invented. I mean, he really did this for another purpose, much more complicated than this. But when you apply it to this, it's a nice trick, and you can generalize it to prove the KK relations in general. So the trick is to realize that this object is a very simple object. So if you have sigma A, sigma B, and you integrate on a auxiliary complex plane sigma, you integrate this object square. Okay, you get exactly one of these factors. So you get sigma A minus sigma B over sigma A minus sigma n, sigma m minus sigma b. That's what you get. Now we can prove the identity by just simply drawing a picture. So we have the sigma plane, and we say the first term is the integral of that function going from sigma 1 to sigma 2. So that's the first term. So let me call it term 1. That gives me this term. This integral over this path gives me the first term. The second term is simply the integral from sigma 2 to sigma 3, and so on. So I go to sigma 4, and I get the next term, and I keep going up to sigma m minus 2, sigma m minus 1, and the last term becomes this integral. So let me call it last, which is this guy. So I ended up with an integral over a closed contour. But now you would say, but wait a minute, how do you know that you could choose this path if we know that there is a pole at the location of sigma n? What happens if you choose this path or this path? It doesn't matter. Why it doesn't matter? Because it's a double pole. Okay? So it doesn't matter which path I chose, so I chose this one. But there is also another consequence. Given that this is a double pole, now I can deform this contour and just show that this whole object is the integral on a contour around my double pole. But that is equal to 0. And we have proven the U1 decoupling identity without using any constraints on the sigmas. Okay? So I hope this is simple enough so that you say, well, yeah, this this twisted space formula makes this property manifest. And you can convince yourselves that all the KK relations actually follow from a picture similar to that. I encourage you to do it, because you will see clearly why you have to choose the transpose of the set beta. Now, the KK relations allow us to write the n-1 factorial partial amplitudes in terms of n-2 factorial. So maybe I should write KK here. I told you these relations were found in the 80s. Now you just reverse the numbers. To have Bern, Carrasco, and Johansson in this paper. So this is the famous BCJ paper that Carlos mentioned during his lectures. In that paper, they did many things, but one of them was to realize that there is even something else that you can do. So n-2 factorial is not the end of the story. You can actually go from n-2 factorial to n-3 factorial. Okay? And the way you do it is that you write your partial amplitudes. You first use cyclicity to put 1 here. Then you use KK to put n here. And now, what they discover is that there is another relation, another set of relations that you can use to put n-1 anywhere you like it. In particular, you can move n-1 next to n. So there is a set of relations that write this formula in terms of the following: n-1n with some permutation w. So this is n-3, a set of n-3 factorial objects. But now the price you pay is a function that depends on Mandelstam variables. And there is some set of permutations, just as we did in KK. Now you would say, well, if you have Mandelstam variables, why is this so exciting? Well, the point is that these are only Mandelstam variables, and therefore are helicity independent. Okay? It turns out that the twisted space formula also makes these relations manifest. Okay? So this is all looking very good. You say, well, the twisted space formula, this Witten's formula, is making all these things manifest. Well, KK is obvious if you did the homework yesterday.
No, not about the I thing.
No, why it must be true? I mean, you want decoupling identity, then you generalize it, and you find these relations. BCJ was a little bit...
I did not do the homework.
You didn't do the homework? Okay, anybody did the homework? Yeah, you see, you put everybody on the spot. No. You say, now my gauge group is not UN, but it's a product of two UN times UM. Now, the same thing must happen, right? In the Lagrangian, the two completely decouple, and you should find new relations.
So those relations, I also expect them at any local.
Yes.
Okay. So I was slightly yesterday. I asked the UN to all those the other ones.
Oh, well, maybe I didn't understand. But the BCJ, the BCJ, they discovered this by playing with objects. No, these Fs are very complicated. I don't remember them.
So it's on a different platform. It's conceptually different.
With the technology I'm going to introduce tomorrow, they both become the same thing. And what these objects are very, very simple. I mean, they are very simple to construct. In the end, they are going to look complicated, but the way to construct them is extremely simple. I'm taking these questions as part of my extra time, right? So, yes. Sorry?
So KK holds that loop.
This relation, I'm not sure it holds at loop level. Yeah. I don't think it's known. Okay. So we see that all these identities, well, I didn't show BCJ, but the identities are very easy to prove using this structure. But there is another thing that can bother you if you knew. Let me tell you what property these things have, and then it's going to bother you. Yeah, it doesn't sound like a nice thing to do, but well, the property that the observation that these two things satisfy, which will make you a little bit uncomfortable, is that these are identities that Young-Mills satisfies without any supersymmetry and in any number of dimensions. So, in any dimension. And therefore, are you unhappy now? Is there something bothering you? And there must be something bothering you. I told you, this twistor string formula is the simplest way we have for showing that these partial amplitudes satisfy these identities. It's almost trivial, as you saw here. But the formula depends on n equals 4 super Young-Mills. It's valid in 4 dimensions. You need a spinor helicity. You need twistor space. You need all that and all. But in the end, it all boiled down to the fact that the amplitudes, that the partial amplitudes, could be written as an integral over n marked points on a sphere. So I have the volume of SL to C. Times, all the magic came from having this factor, times something permutation invariant. So could it be that there is such a formula for amplitudes in Young-Mills in any number of dimensions and without any supersymmetry? Now, we don't have spin or helicity. We don't have supersymmetry. So whatever this is has to be something that depends on the momentum vectors. We don't have lambdas and lambda tildes. We don't have lambdas and lambda tildes, and therefore you have to bring back the polarization vectors and the sigmas. Okay? And I'll end here. Yes, it wasn't a joke. I'm ending here. You'll have to come tomorrow at 9 to find out the answer. Exactly. We don't have helicity, so there is no maximally helicity violating. So whatever formula we have, if that formula exists, it cannot have this label, because this label doesn't exist in higher dimensions. It has to be a formula that unifies all these different things into a single object. All helicity sectors will have to be unified. So if you do a calculation of Young-Mills amplitudes in 5 dimensions, from that single calculation that you did there, you should be able to obtain all the different helicity sectors in 4 dimensions. So it has to be something rather powerful, right? Because it has to unify everything. So that's a very good question. And that's part of the reason why it took so long to find, because everything was hinting to the fact that this was extremely special. And after all, this is n equals 4 super Young-Mills. The harmonic oscillator, now the Ising model of this century, right? So it's not surprising that n equals 4 super Young means we have beautiful formulas associated with it. But then just good old non-supersymmetric Young meals in any number of dimensions. Why would there be anything nice? Right? Any other questions?
So from the point of view of string theory on twistor space, what are these things calculated? Like string scattering or something? Or?
Yeah, from the point of view of very good, very good. So this object is nothing but the correlation function of vertex operators in this string theory. So exactly what Carlos was explaining, but now done in this topological B model.
So you don't have to take like an alpha prime to 0 limiter?
No, the topological B model is not a full string theory. It only has a finite number of degrees of freedom, and they exactly match on that target space that I mentioned on CP3/4, the degrees, the fields that the string theory propagates are exactly those of n equals 4 super Young meals. So you don't have massive states. So you don't have to take alpha prime to 0. Very good question, yes. This is all at 3 levels, yes. Yeah, there are some complications with that related to the fact that it's not that easy to write a measure for that. So that's a long story, but it's still unclear.
You started with an expression which comes without any symmetry, and you landed on an expression which has symmetry that equals 4, presumably because there's a symmetry.
Exactly.
Well, what was the reason that we couldn't just have string theory that wasn't in a critical dimension? Like, what would
Well, simply that you cannot write something that is conformal invariant. I mean, the central charge will not cancel.
yeah, but what does loop level on the motion correspond to?
Well, this correlation function on the sphere is the full partition function. It's a full correlation function. You see, there is something funny in string theory. To compute the 3 leveling in space-time, you have to do a full path integral calculation. You never realize it because it's a conformal field theory, so we have techniques to do it. But if we didn't know any techniques and so on, well, it would still be a free theory in the Lagrangian, but you would still have to do your calculations order by order. Yeah, you shouldn't be surprised. I mean, we have, in conformal field theory, we have techniques for computing these correlation functions in 2 dimensions completely, exactly, right? I mean, it's surprising if you don't know conformal field theory because you'd say in 4 dimensions, it's very hard to compute things unless, of course, you have integrability. But in theories where you don't have the help of integrability, we don't know any quantity at any finite value of the coupling to all orders in perturbation theory and so on. But in 2 dimensions, we do. These objects are. Is that clear? I mean,
I guess I just don't really see what the difference is.
no, it's a relation between a string theory and the field theory in the target space, right? At 3-level calculation in target space, the string theory does the calculation as a full partition function on the sphere. It's not a perturbative calculation on the world sheet. Okay, so it's not that I do a 1 loop calculation in the 2-dimensional conformal field theory, and that 1 loop calculation corresponds to something there. No, you do the full calculation there.
Surfaces here and correspond to loops.
It should. Yeah, if you only knew how to write the measure, yes. Yeah, so that's the problem. Try to write a holomorphic measure over the model space of maps of degree D from a genus 1 Riemann surface to CP3/4. So take the question to your friend, to your mathematician friend, and say, well, okay, here. This was my homework problem for one of the classes. Can you help me out? No, I think that's solved. There is something that Skinner and Casali found, which is
But that was progressive.
no. It's called. It's not published, but it's solved. Yes. It's very funny because it's called the comb structure. Well, it's just that there is a way to introduce some trace structure that ends up giving you amplitudes in these bases for the color structure. But note that this was discovered by, well, it hasn't been published, but it was discovered by Casali and Skinner. So it's a CS structure. I don't know if they did it on purpose, but I just find it funny. So it's at the instead of using traces, you use color structures, and there is a way to introduce a projection that kills that kills the multi-trace things.
But if you would like to do at loop level, for example, if you would like to trace, you would expect perhaps.
Possibly, yes, but they did this for the ambitwister version. So, but presumably it would do the same thing here if you knew how to do it in 4 dimensions.
This was an important open problem, right? So what you are saying is that there is an or it was not important.
No, it's an important problem, but if you knew how to write the measure, but nobody knows how to write the measure.
Just about this thing, about reliable, given just reliable.
Yes, but they became a little bit more ambitious. So they really want to use it for the ambitwister formula to get the loop amplitudes correctly. And we have to wait until the paper is out. Yes. Okay. Any other questions? No. So let's thank the speaker.